Yes, hello everyone. In the previous class, we discussed about the source follower circuit, where you are seeing this is the common drain or source follower circuit, and this is the input output characteristics of the same. Okay, so this is the input which is shown in a dotted line, and the output is following the input after a certain voltage, which is threshold voltage, and we have calculated the expression for the gain, which is AV is nothing but GM into RS upon 1 plus GM plus GMB into RS. So this is what we have come across. And second, we come across what is the output impedance of the source follower. Okay, so we also calculated what is the output impedance of the source follower, which happens to be 1 upon GM plus GMB. So now continuing with this, we will follow the another characteristics where we plot the gain versus input characteristics of the same source follower circuit. This is gain versus input. So here what happens, the voltage gain begins from 0 for V in less than or almost equal to threshold voltage. The gain starts or the output starts following after this threshold voltage, right? Okay, and up till this point what happens, the transconductance GM will be equal to 0 at this point, and after threshold voltage this output monotonically increases and also the gain, fine. So it will go like this, and the maximum gain of the source follower is 1. So, okay, so this is the gain versus input characteristics. So as the drain current and transconductance also increases, the drain current and the transconductance also increases, the gain approaches up till 1, where you get it as GM upon GM plus GMB. If you take GM common and approximate it, you will get it as 1 upon 1 plus eta, where eta is GMB divided by GM. Okay, and this itself slowly decreases with V out, and this gain will eventually reaches unity. But before, a typical allowable source bulk voltage, the source bulk voltage means this eta remains roughly around equal to zero point 0.2, right? So as we have got the result for the gain as GM into RS upon 1 plus GM plus GMB into RS. So in this what happens, even if RS approaches to be very large value, okay, so the voltage gain of the source follower will not be equal to 1 even if it reaches infinite. Okay, so here what happens in the circuit, if you observe, the transistor does not enter into triode region if V in is below threshold voltage, right? So this is the another observations what we are supposed to discuss in this common drain or the source follower circuit. And continuing this, we will solve one problem on the same. Say for example, uh, we have a source follower circuit. We will solve an example on this. So we have a source follower circuit. So this is V in, and this, say for example, we have current which is drawing from, we have a load here which has a constant current source, can also be represented. So eventually what we are doing, we are making the RS to be infinite, which is an ideal current source kind of. Okay, so here this is V out and this is VDD. Okay, Suppose this is the force follower what we are considering, and this is the transistor M1, and if this transistor has a W by L of, say for example, W by L of 20 divided by 0.5, the width is 20 micrometer divided by 0.5 micrometer, the length, and the current I1 what it is drawing, say for example it is 200 microamp. Okay, and the threshold voltage of this transistor M1 happens to be 0.6 volt, and we can have another few specifications like Fermi level 25F to be 0.7 volt, and we can have mu n COX to be as some 50 microamps per volt square, and gamma as 0.4 volt square. Okay, so the question here is, so first question here is calculate V out for V in to be 1.2 volt. Okay, this is the first question. We have to find out what is the output voltage for input voltage to be 1.2 volts. Okay, this is the first question. So we will try to solve this. Since the threshold voltage of M1, you see now the body of this and the source terminal of this transistor M1 are at different potential, and hence there will be obviously a body effect for this. So since M1 depends on the output voltage of M1 depends on V out, the threshold voltage of M1 depends upon V out, so we have to perform a simple iteration to know that how that threshold voltage is varying and how that change in threshold voltage will affect the output voltage. That is what we have to do here. So that we note that the expression for ID, what we have, ID is 1 by 2 mu n COX W by L into VGS minus VT. VG is V in minus Vs is V out, and Vth whole square. This is the current expression what I have taken considering the M1 to be in the saturation region. Okay, so this explains that what is the effect of the threshold voltage, or what will be the output voltage for this. We can predict what will be the output voltage for this, taking this term on this side, say for example V in minus Vth minus V out whole square is equal to 2ID divided by mu n COX W by L. Okay, so here substituting the value of V in as 1.2 volt, the threshold voltage given is 0.6. We have to find out what is V out. Okay, so the ID is 200 micro, which has been given, divided by mu n COX is 50 micro, and W by L is also given, which is 20 by 0.5. The ratio has been given. The only unknown term is V out. So by evaluating this, we obtain V out to be as around 0.63, sorry, not 0.635, V out to be as 0.153 volt. So this is the output voltage what we get from this expression. Fine. If you solve for V out in this expression, we will get V out to be as 0.153 volts. Okay. So this is the output voltage with the threshold voltage of 0.6. But as we see here, M1, the transistor M1 has the body and the source terminal are at different potential. Hence there will be change in the threshold voltage, and this change in threshold voltage will obviously affect your output voltage. So to find out what is the change in threshold voltage, we have the expression VTH is VTHO plus eta into 2 phi f plus VSB in the square root minus 2 phi f in the square root. This is the expression of the threshold voltage what we have, and this solving for this we get VTHO is 0.6 plus eta is 0.4, 2 phi f is 0.7 plus VSB. What is VSB? The source terminal is V out itself. Okay, VSB means VSB is nothing but Vs minus Vb. So Vs is V out and Vb is nothing but what? 0. So VSB is nothing but V out. So V out happens to be 0.153, okay, minus this of course in the square root and this 0.7 again. Okay, so solving for this you get a threshold voltage to be as 0.635 volts. So this is the threshold voltage what the changes has occurred because of the body effect, which means the body and the source terminal being at the different potential. Okay, so here what happens, this indicates, this is the earlier the threshold voltage was 0.6, now the threshold voltage is 0.635, which means that V out is approximately 30 millivolts less than we calculated. What is that we calculated? 0.153 volt. Okay, so this is 35 millivolts less than this actual what we have calculated. So your actual V out happens to be 0.119 volt. So this is the actual output voltage of the given circuit. So this is one of the question that is asked in the circuit. Again continuing the same, we will continue the same for the next question for the same circuit what we have drawn. So this is the I'll just redraw the circuit. This is the circuit what we had. Okay, this is M1. So with this, this is VDD. Okay. So this is the same circuit what I have continuing the same problem with M1 having W by L of 20 by 0.5 and I1 to be the current which is drawing from VDD is nothing but 200 microamps and with the same specification. Okay. So in the second part of this question is, if I1, what we have this I1 is implemented using another transistor, say for example M2. Okay, so if we implement this current source I1 with another transistor, say for example M2, in that case what will be the minimum value of W by L of second transistor? Okay, for which of course this transistor should also act as saturation region or a constant current source, M2 remain saturated. Understood? So this is the second question. Continuing the same, in the circuit, if we replace this current source I1 with the another transistor M2, so what should be the value of W by L of for that transistor to retain this to be in the saturation region, transistor M2 to be in the saturation region. So we will draw the circuit which has been asked for the second question. So this has to be externally biased. This is the M2 what it is asked for. This is V in, this is VDD, this is M1, for which the specification of M1 is given to be as how much? 20 by 0.5. So now the next question is, what is the W by L of transistor M2? Okay. So now coming to this question, second question, since the drain to source voltage, which is nothing but what? V out. The drain to source voltage of M2, which happens to be V out, is equal to how much we have obtained? We have obtained is as 0.119. You see here, we have obtained the V out to be 0.119 considering the body effect as well. So that will be the that itself will be the drain to source voltage of second transistor M2. Okay. So now this transistor M2 will be saturated if VGS minus VTH of second transistor is less than or equal to 0.119 volt, which is output voltage. Okay, and the current what we have, ID we have it as 200 microamps. Okay, so now solving for this, what do we get? The current equation, ID is equal to mu n COX 1 by 2 mu n COX W by L of second transistor into VGS minus VTH whole square. This has to be approximately equal to 0.119. ID is anyhow 200 micro is equal to 1 by 2 into this mu n COX is 50 micro amps per volt square. W by L of second transistor is what we have to calculate. This VGS minus VTH is nothing but minimum, it should be 0.119 which is equal to output voltage. So this will be 0.119 whole square. Okay, so on solving this, what we get? W by L of second transistor. So if I calculator here, so this is 2, 25, 1, 8. Okay, so 8 divided by 0.119 whole square, which happens to be 0.119 whole square, this one 0.01416. So 8 divided by 0.01416, you get it around 564.97. This is the ratio what you get. So making it approximately equal to divide by 0.5. So we will divide both numerator and denominator by 0.5. What you get is divide by I get 282, so it is approximately 282.5 divided by 0.5. Okay, so this is the value of W by L of second transistor, approximately value of W by L of second transistor. Fine. So this is one of the example what we have come across. So now continuing it for the next circuit. Okay, we will move on to the next circuit, which is common gate amplifier. Right? Common gate. So common gate means the gate is common for both input and output. So this is gate, so this is V out, and this is RD, and this is VDD. Okay, and this is the source terminal, this is drain and this is gate, and we are giving the input to the source terminal. Input is given to the source terminal over here, this being a positive with respect to, right? So here this is the common gate circuit. So this in the common source amplifier and the source follower, both the circuits what we have discussed so far, the input is applied to the gate of the MOSFET. Okay, so now here in this common gate we are giving the input to the source terminal. That is the important point to observe here. So VB, which is a DC bias, is given to this MOSFET to make sure the device to be in the saturation region, and for the AC analysis this will be the ground, it will be in AC ground for the AC analysis. Okay, so the gate is connected to the DC voltage to establish a proper operating condition, note that, and the bias current for M1 flows through the input signal through source. Okay, so now and we also, if we analyze the large signal analysis of this circuit, V in versus V out. Okay, so what happens here in this, for a certain value, for example VB minus VTH, VB is nothing but the bias voltage what we are giving. Okay, so now for your input V in greater than or equal to VB minus VTH, okay, VB minus VTH, this makes what happens, the transistor M1 to be in off state, because so if V in is greater means V in means it is actually to the source terminal. Okay, for the device to turn on, your VGS should be greater than 0.7 volt threshold voltage. Okay, should be greater than the threshold voltage. Here VG is VB and Vs is input in this case. If V in is greater than VB minus VTH, the device will be off. The gate voltage will be very less compared to the source voltage, and the device will be off. Okay, and when the device is off, what will be your output voltage? Vout will be equal to VDD. Okay, so you know that if we apply the KVL to this output loop, this is one branch and this is another branch, this VDD KVL to the output, it is VDD is distributed across ID RD plus V out. This is the current ID flowing through the RD and V out. So if M1 is off, ID will be 0, hence your V out will be equal to VDD. Okay, So for the V in, this is your in V in what you are varying. For the V in greater than uh, VB minus VTH, this will be VDD. It will be like this. Understood? So if V in decreases from this value, okay, I mean if V in is less than VB minus VTH, what happens? The device is on and ID starts flowing, and obviously your VDD V out is VDD minus ID RD. So now what happens to your V out? V out starts decreasing. Okay, V out starts decreasing. Okay, so when it is less, the device is on, and the V in is very much less, so that if M1 is in saturation region, that means we have decreased V in, so that M1 is in saturation region, and V out eventually drive M1 again to be in the triode region. Okay, so if this device is in saturation region M1 for an amplifier, so what we have V out is equal to VDD minus IDRD. ID I will replace it by the current corresponding to that, half mu n COX W by L into VGS minus VT. What is VG? G is VB, VG, S is what? V in minus VTH whole square into RD. Okay, so this is the expression for output voltage when the input is less than VB minus VTH, ensuring that the transistor M1 in saturation region. Okay, so now this is the equation what we have. So if we for the small signal analysis, we can express this expression partial derivation with respect to V in. So dou V out by dou V in is equal to 0 minus 1 by 2 into mu n COX W by L into 2 times of VB minus V in minus VTH. This is 2x into differentiation of x is, this is RD as it is, differentiation of this internal terms 0 minus differentiation of V in with respect to V in will be 1 minus differentiation of VTH with respect to V in. Okay, so solving this further, this two will get cancelled. You have what? Minus mu n COX W by L, okay, into VB minus V in minus VTH into RD. This is RD corresponding to this, and taking this negative common, 1 plus dou differentiation of this threshold voltage with respect to V in will give you eta value. This we have already defined or derived it earlier. Okay, and this entire term is nothing but the transconductance of the MOS device with this configuration. With this configuration means the common gate configuration. Okay, so this will be GM. So this plus and this minus will become plus, and this is GM into RD into 1 plus eta. This is the small signal gain for the common gate amplifier. Okay, and note that here the gain is positive. Okay, and interestingly the body effect increases because the body and the source terminal will be at the different potential, so you have an equivalent transconductance on the this common gate stage. Okay, this is the expression of gain. So we'll find out what is the output voltage of this common gate. Common gate containing the same circuit. This is the source resistance with, this is the input signal what we are giving V in to the source terminal through resistance Rs. Okay, and this is VB and this is V out, RD and VDD. Okay, so here we know the output impedance is very large. So for the finite R naught, for the finite R naught of this MOSFET, we will find out what is the output impedance. Okay, what is the common gate configuration. Fine. So to find this, we have to plot the small signal model for this. So we have, this is GM into V1. Say for example, this is V1. This is gate terminal. This is drain terminal. So the gate is connected to AC ground for the AC analysis, and from the source terminal we have RS and then V in. Okay, so here again we have R naught, which is nothing but the channel length modulation. So along with this we have the body effect GMB, which is a function of VBS, which is a function of VBS, and this is the drain terminal which is connected to RD. This is V out. Okay, so this is the small signal equivalent for the common gate circuit. Okay, so now initially current flowing through current flowing through RS. So for example, the current flowing through RS is, this is the, we are calculating the output voltage. So this is the I out, what we are getting from corresponding to the output voltage V out. Okay, and this is flowing through this here. But here we have input voltage, and because of this input voltage we have the current flowing through RD. First the current flowing through RD, we have this is the current flowing through this I out. I out is nothing but what? V out by RD. I out is V out by RD, and it is the same current which is flowing through the RS. Now with respect to RS, we have this RS, current flowing through the RS will be equal to minus V out by RD. Okay, because I out means this is the I out. Okay, this is V out, this being the positive, and this will be the direction of I out. so it is not in this direction. This is the direction of I out. Okay, so hence the current flowing through the RS will be minus V out by RD. I hope everyone understood that. So this is V out, you see this is the V out positive terminal, and the current I out will be flowing in this direction. So the current will be flowing in this direction. So with respect to RS it will be minus I out, okay, which is minus V out by RD. So this is one of the current what we have obtained, and another, the current flowing through R naught, the channel length modulation what we have R naught, current flowing through R naught is given by this is the total current. The total current is nothing but I out, it is in the opposite direction, which I will write it as minus V out by RD. So this is the total current. So the current flowing through only R naught is the total current minus this current and this current, minus this GMB current and GM current. Okay, so which is minus GM into V1 and minus GMB into V1. Okay, so this is the current flowing through the resistance R naught. So the current flowing through the resistance R naught is IR naught. What I have taken is like this. Okay. So now finding out my output voltage. V out is nothing but the drop across this branch plus RS branch and V in. Okay, so what is my V out? V out is the drop across this branch what I told, which I will take it as across R naught. So it is IR naught into R naught minus V out by RD. This is the current flowing through the RS. Okay, so the drop across this RS is RS into minus V out by RD. This is the current into resistance which give you the voltage plus V in. So this 3 branch or the drop across this 3 branch gives you the output voltage. Okay, so substituting its corresponding R naught and substituting and also we can have at the input side. So we will take this as equation 1. So at input side, so V in, what is V in? Or applying KVL to this input loop, KVL to input loop, which is nothing but V1 plus the drop across voltage across RS plus V in. Okay, so these 3 voltages is the KVL to the input loop. What are those? V1 plus IRS. IRS is nothing but minus V out by RD into RS plus V in. This is equal to 0. So we can write this as V1 is equal to V out by RD into RS minus V in. This we can take it as equation 2, and this is the current equation what we are going to use it for IR naught. So substituting all these in the equation 1, that is this V out equation what we have. So V out is equal to I out into R naught. R naught into I R naught. What is I R naught? I R naught is this minus V out by RD. So minus GM plus GMB. I will take minus common because if I take both common, I will get GM plus GMB into V1. Okay, I will substitute for V1 from equation 2. What is my V1? V1 is V out by RD into RS minus V in. Okay, so this whole thing is my IR naught. Okay, so the second term as it is minus V out into RS by RD plus V in. Okay, so now we have the expression all in terms of V in and V out. Okay, so we are finding out what is the gain for this. So it follows that V out by V in happens to be GM plus GMB into R naught plus 1 whole divided by R naught plus GM plus GMB into R naught into RS plus RS plus RD into RD. This is the expression for the gain of common gate amplifier. Okay, and here we observe that in the common gate there is the body effect is very high. The body effect is very high. Fine. So this is the expression for the gain. So finding out what is the output impedance. Fine. What is the output impedance? I hope everyone is clear up till here. Continuing to find out what is the input impedance and output impedance. First we'll find out what is input impedance. First we'll go with the input impedance. So this is the common gate VDD and this is VB, and we have finite output impedance considering the finite output impedance of the MOSFET, and since this is the input, so this is the input resistance what we are supposed to find out. Okay, so writing the small signal model for this, GM into V1 and R naught GMB into VBS. This is RD. This is drain terminal. This is gate terminal which is connected to ground for common gate, and we are giving the input. This will be the V1. We will consider GMV1 corresponding to that, and this is the source terminal where we are giving the input signal. Since we are finding the input impedance, we will consider this is the voltage at the input terminal, and this is the current corresponding to this voltage at the input terminal, so that we have to find out what is the ratio of Vx divided by Ix to find out the impedance corresponding to this. Fine. So this is the small signal model. So in this we observe the this V1 what we have. V1, if we tilt this Vx, this in magnitude of V1 and Vx will be the same, but here V1 will be minus Vx because it will be tilted, it becomes opposite direction. Okay, so since V1 will be equal to Vx, and Vbs is nothing but Vb minus Vs, which is again the same, 0 minus Vx, so Vbs will also be equal to minus Vx. Note that, minus Vx. Okay, and again we will find out what is the current through R0. So the current through R0 is Ix is the total current from the Vx, and this is again the total current Ix which is going out of this three branches, GMV1 R0 and GMB VBS, to the load which is Ix again. Okay, so the current through R0 will be equal to the total current Ix plus, since all are in the same, means both Ix will be in the opposite direction, Gm into V1 plus GMB into VBS. Okay, so all the terms will be positive because you see Ix is flowing towards upwards. Okay, so the current flowing through the R0 is given like this, which is opposite to that of Ix. Okay, so I can take it as minus Ix minus GMV1 or minus GMB VBS, which will be equal to minus this, both will be equal to 0, and Ix minus Gm plus GMB into Vx, substituting this V1 and VBS for Vx, and V1 as Vx and VBS as Vx, I mean minus Vx. Okay, so now we have the total voltage Vx. Finally, adding up the voltage across R0 and RD, we get RD into Ix plus R0 into R0, which is the current flowing through this, what we have got here, Ix minus Gm plus GMB into Vx. Okay, so this is the equal to Vx, the total voltage Vx. So this, adding up the voltage across R0 and RD, which gives us RD into Ix plus R0 into Ix minus Gm plus GMB into Vx will be equal to Vx. So solving for Vx upon Ix, we get what? RD plus R0 divided by 1 plus Gm plus GMB into R0. So this is the input impedance of the common gate circuit. So if I separate this as RD upon 1 plus GM plus GMB into R naught plus R naught by R naught will get cancelled. So if we take LCM, this will get cancelled, GM plus GMB into R naught. So this R naught will also get cancelled, 1 upon GM plus GMB into R naught. Sorry, this R naught is getting cancelled. GM plus GMB. Okay. So here, this is the input impedance of the common gate circuit. So this result what we get here, we can approximate this GM plus GMB multiplied with R naught to be very much greater than 1. You know, this R naught into GM plus GMB will be greater than 1. So this results reveals that the drain impedance, which is divided by GM plus GMB into R naught, is what we see from the source terminal. This is particularly important in the short channel device because of their low intrinsic gain. Okay. So if RD equals 0, then your Vx upon Ix, or the input impedance, will be just R naught upon 1 plus GM plus GMB into R naught, which I can write it as 1 upon R naught plus GM plus GMB, which is simply the impedance seen at the source of the source follower, which is a predictable result when RD is equal to 0. Fine. So this is about the input impedance. Fine. To find out the output impedance again, we will finish off with this output impedance of the common gate circuit. So this is very simple. We will just analyze with respect to what we have known. So we have RS, this is RD, and this will be the VO terminal, and this is VB. So since we are finding out output impedance, so we will apply the voltage Vx from the output terminal. What this is the output terminal, and this is Vx, and the current due to Vx will be obviously Ix. Fine. Vx will be obviously Ix. So this is the impedance what we have to find, that is Vx by Ix will be your output impedance. Okay. So in the previous what we have discussed, the common source amplifier with the source degeneration circuit, I hope you remember, that is in the previous class we have discussed about the common source circuit with source degeneration circuit. This is nothing but the common source amplifier with the source degeneration circuit. So here what happens, the output impedance of the common source amplifier with source degeneration resistance Rs, we have obtained it as 1 plus GM plus GMB into R naught whole multiplied by Rs plus R naught. So this is the impedance of the common source amplifier with the source degeneration circuit. So now for the common gate, what happens, this is the same configuration with the source resistance over here. So when I plot the small signal model for this entire thing will be in parallel with this RD, okay, where this VDD terminal will be an AC ground. So your R output, what we are calculating, R out will be this common source with source degeneration circuit parallel with RD. This itself will be your output resistance of the common gate circuit. I have just analyzed it, means intuitively what we have discussed from the previous discussion. We have directly arrived at the output impedance of this, considering the impedance of this MOSFET with source resistance, which we have calculated earlier in the common source with source degeneration circuit, happens to be 1 plus Gm plus Gmb into R naught whole multiplied by Rs plus R naught. So this is the one, and for this common gate, this is the what we are calculating the impedance at this terminal, which is V out. Vx by Ix is nothing but this impedance parallel with RD, So this is what the output impedance of the common gate circuit. Okay, so this is about the common gate circuit. So I will just stop it here, and in the next class we will discuss about the cascade stage.